Good morning, everybody. Welcome to Unit 2 of AP Calculus. We're going to work through the first lesson in the guided notes packet for Unit 2. If you were in the even addresses group, I gave this to you right before you left class yesterday. If you're in the odd addresses group, I forgot to give you the guided notes packet last week, so I posted it on Google Classroom. You can go ahead and print out the whole thing, or just print out topic 1, which is pages 1 through 4, and I'll give you the rest of the packet when you're in class tomorrow. But either way, please have at least topic 1 printed out so we can fill it in here as we go. Unit 2 is all about something called differentiation, which is a word we'll talk about what that means a little bit later on. But we're just going to get into some basic ideas that we'll be using really for the next several units today. So we're starting with a question. What is a tangent line? So a tangent line, I'll just give you the definition right here. A tangent line is a line that, quote, just touches a graph. So it's just touching a curve at one point. And it matches the curve's slope at that point. And it matches the curve's slope at that point. Whoops. So it's a line that's just touching the curve at one point, and at that point, it's matching the slope's curve. So just looking at a couple examples of tangent lines. Here in this parabola right here at the vertex, this line is just touching the point at the vertex, and the slope there is pretty much 0. It went with a positive slope for a while, but then it leveled off before it goes back to a negative slope. Here on this second example, at point P, this line is just grazing that curve once. It does cross the curve. That's okay, because it's approximating the slope right there at that point. That curve is sloping at the same slope as that line. And then here at point P, this line is approximating that slope of the curve. Notice it touches the graph more than once. There'd be another intersection point down there. That's okay. We're only really concerned about the line being tangent at point P, where it's just touching and matching the slope at that point. So the bottom of this page and onto the next page, there's a few misconceptions about tangent lines. If you're interested, you can read through those on your own. But as long as we know this definition, I think we should be pretty good with what a tangent line is. Now, the reason tangent lines are important is because it's a lot easier to find the slope of a line than it is to find the slope of a curve, because curves don't really have one slope throughout. Like we talked about with this parabola, there's a pretty steep positive slope right here, but then if I get here, it's still a positive slope, but not as steep. And then on the other side of the vertex, now we're talking about a negative slope, and then an even steeper negative slope. So curves don't have just one slope like lines do. And slope is going to be really important because we talked about at the beginning of the year, calculus is the study of change, the mathematical study of change. And a slope is essentially the rate of change. How fast is something changing? And that's going to be one of the big ideas of calculus, is taking a function whose graph might be a curve and being able to talk about the rate at which it's changing. So we're essentially talking about slope. We're going to use this idea of a tangent line because it's a line. It's easier to find the slope, but it matches the curve of the slope at one point. So we're going to be working with slopes of tangent lines for a while, for probably all of units 2, 3, and 4 at least. So like I said, there's some misconceptions about tangent lines here. If you want to check those out, go for it. But as long as we know that definition we wrote down, we should be pretty good. So I'm going to skip down to the activity here called the tangent line problem. The tangent line problem says begin with this graph y equals f of x, this function. Let's begin with an arbitrary point and call it c f of c. So it's already graphed that for us. That's this point right here. Then let's choose another point on the curve somewhere to the right of that point. And it said preferably close to the right edge. So just pick a point somewhere over here close to the right edge and put another point. And it says we're going to call that point x, f of x. Remember, f of x really just means y. So we're basically just calling this point x, y. Now connect these 2 points. So I'll connect those 2 points with a line. What we've just drawn is called a secant line. A secant line is a line that just connects 2 points on a curve. So it's different from a tangent line. A tangent line is only going to be touching the curve at 1 point. A secant line is connecting 2 points. It's asking us what is the slope of this secant line. Well, we need to remember our slope formula. Y2 minus y1 over x2 minus x1. So our y coordinates here are f of x, f of c. So f of x minus f of c over x2 minus x1. So x minus c. This would be our formula for calculating the slope of this line. Now, how well does the slope of this line match the slope of the curve? Well, it kind of depends where we're talking. It looks like it might match the slope of the curve here, but, really I'm concerned about this point, and it doesn't do a very good job of matching the slope at that point. That's more of almost a horizontal slope. So with that secant line that we drew, we didn't do a great job approximating the slope at point C. So step 2 says, okay, well, let's take that point and move it a little bit closer. Let's move it maybe here. So let's move x, f of x, closer to c, f of c. Now if I draw my secant line again, well, this time my secant line does a better job approximating the slope of the curve. But remember, we're really concerned in the slope at this point. So it's still not really spot on. It's closer, but it's not quite there. It's asking us, is there any difference in the way we calculate the slope? Well, no. It would still be f of x minus f of c over x minus c. So we got closer to the slope of the tangent line, but we're still not quite there. So step 3 says, since we're having such a blast moving that second point closer, let's move it so close that it's almost touching C. So I'm going to put my second point right here. So super duper close to C. Now if I connect these points, I'm getting a line, a secant line, that comes very, very close to what the slope of the tangent line would be. So my tangent line would be, just grazing this at that 1 point. So you can see those lines are pretty much the same line. So as our 2 points get really close together, the secant line almost turns into a tangent line. So when I found my slope here, I would do m equals f of x minus f of c over x minus c. I would be really close to the tangent line. And in fact, if I move that point even closer, I could get even closer to the tangent line. So the question it's asking us is, how could we perceive this slope using a very important concept from Unit 1? What we're really doing here is a limit. We're trying to get these 2 points really close together and then find the slope. So what we're actually doing is the limit as x approaches C, as the x coordinates get really close together, as this coordinate x is approaching this coordinate C. So the 2 points are getting super close together. And what are we finding the limit of? Well, we're finding the limit of the slope formula. F of x minus f of c over x minus c. So if we can find the limit as the 2 points get super close together of the slope, that actually will end up being the slope of that tangent line that we're going to be trying to find. So the limit as x approaches c of f of x minus f of c over x minus c will give us the slope of the tangent line. On the next page, it gives us the definition of a tangent line. It's basically just saying if f is defined on this interval, and if this limit we just talked about exists, then the line through those points is the tangent line. So now we're not even saying, well, it's going to get really close to being the tangent line. This is telling us that actually is the tangent line, which that's going to be really helpful for us to know. So we're just going to do a couple example problems here trying to use this formula to find the slope of a tangent line. So in example 1, it says the slope of the graph of a linear function. Well, this is super easy to do because this is already a line. This is y equals mx plus b. So we actually already know the slope. The slope here is just 2. The slope is 2 because it's a linear function. It doesn't matter what the x-coordinate is. A line has the same slope everywhere. So the slope here is 2. But just so we get the practice using this formula, we're going to do this problem using that formula, and we should know the answer we need to get is 2. So let's give it a try. So we're specifically concerned with this x-coordinate. That's going to be our c. That's the point that's not moving. We're essentially going to pick a different point moving closer and closer to that one. So whenever we are doing the limit as x approaches c of f of x minus f of c minus c, that c is going to be 1 here. So c is 1. So just plug that into the formula. This is the limit as x approaches c, which is 1, of f of x minus f of c, so f of 1, over x minus c, which is 1. So notice if I try to do a direct substitution here, if I plug in 1, that would be f of 1 minus f of 1, which would be 0, over 1 minus 1, which would be 0. It would be 0 over 0. Remember, that means we need to do something to simplify our function. So I'm going to start actually evaluating some y values here. So this will equal the limit as x approaches 1. Well, what is f of x? It told us right here. F of x is 2x minus 3. So I'm going to plug the function in there. Minus f of 1 means plug 1 into the function. So 2 times 1 minus 3 would be 2 minus 3. That's negative 1. So for f of x, I just plugged in the function itself. For f of 1, I evaluated f of 1 and got negative 1. So continuing to simplify, the limit as x approaches 1 of, well here, negative 3 minus negative 1. That's really negative 3 plus 1, so that's 2x minus 2. And then I can factor out a GCF of 2. And then x minus 1 will cancel out. So I'll be left with just the limit as x approaches 1 of 2, which is 2. And that confirms just what we set up here. We knew the slope was 2 already, but we used the slope formula and we got the correct answer. So let's try it with one that is not a linear graph. Let's do one. This is x squared plus 1. This would be a parabola. So find the slope of the tangent line to the graph of f of x equals x squared plus 1 at the value x equals 1. So again, this is going to be our c. So when we're doing the limit as x approaches c of f of x minus f of c over x minus c, every time we see c, we're going to plug in 1. So we've got the limit as x approaches 1 of f of x minus f of 1 over x minus 1. And again, if we tried plugging in 1, we'd get 0 over 0 again. There's going to be some stuff to simplify. So this will equal the limit as x approaches 1 of, well, what was f of x? It's x squared plus 1. Minus, what would f of 1 be here? Well, it would be 1 squared plus 1, so 2. F of 1 is 2. A little bit of simplifying. This numerator would simplify to x squared minus 1 over x minus 1. And then the numerator here is a difference of squares. So we could factor that down to x plus 1 times x minus 1 over x minus 1. And we see, again, we have a factor that cancels out. So we should end up with the limit as x approaches 1 of just x plus 1. And now we can do a direct substitution. This would also equal 2. So the slope of this parabola at that x value 1 would be 2. So this limit equation we've been working with is used so frequently in calculus that it has a special notation and a special name. Whenever we are writing this limit formula, we call that f prime of c. F prime of c, that little apostrophe. It's called a prime mark here. So f prime of c, and we use that to denote the slope of the tangent line. So whenever you see something that says find f prime of c, that really is saying find the slope of the tangent line at whatever x coordinate is in the parentheses there. And we use that so much it has its own name. We call that a derivative. F prime of x is the derivative of f of x. And we will be working with derivatives pretty much the rest of the school year. So this is a very, very big, important topic in AP Calculus. Now, if we go on to the last page here, there's just one more example of a multiple choice question here. It says, if f is a function for which the limit as x approaches negative 2 of f of x minus f of 2 over x plus 2 equals 0, which statement must be true? So before I even get to the choices, I'm going to try to look at this and figure out what it's actually saying. So I recognize that derivative notation here, that slope of the tangent line. I'm doing a limit of something that is basically the slope formula here. So what is c? Well, c is negative 2, because that's what x is approaching. So c is negative 2, and what do we know about the slope? Well, it told us this slope is equal to 0. So at c equals negative 2, the slope is 0, because it gave us this slope of the tangent line and said it's equal to 0. Well, what does the slope of 0 look like? That's a horizontal line. All right, so I have some information here. Let's go through the choices and see which of these match up. X equals negative 2 is a vertical asymptote of the graph. Well, I'm not sure that makes sense, because at a vertical asymptote, the slope can't be 0. So the slope would be kind of almost undefined there. So I don't think negative 2 is a vertical asymptote if it has a slope of 0. So it's not A. B, the function f is continuous at x equals 2. Well, do we know anything about x equals 2? All we know about is x equals negative 2. So this function might be continuous at x equals 2. We have no way of knowing. And since we're looking for what must be true, we can't say that's true. The derivative of f at x equals negative 2 exists. Well, this thing right here, this is, we just said, called a derivative. And we said it's equal to 0. So if it's equal to 0, it must exist. So that seems like it must be true to me. The derivative, if we know what it's equal to, it definitely exists. But just to be safe, let's check choice D. F is not defined at x equals negative 2. Well, if it has a slope, it must be defined. If there just wasn't a point there, there couldn't be a slope there. So f is not defined at x equals negative 2. I don't think that's true here because it has a slope. So the answer here should be C. The derivative of f at x equals negative 2 exists. We know it exists because it told us that it was 0. So hopefully you're able to follow along. Please let me know if you have any questions with anything we looked at here today. I'll be at the school all day today until 3 o'clock, so you can feel free to email me. If you want to hop on a Google Meet, we can talk about anything you want to talk about. And then I look forward to seeing the odd addresses group back here tomorrow and the even group next week. Let me know if you have any questions, and I'll see you later.